All right. Hello, everybody. Welcome to the fourth PGSS. Today, we have Alisher Duspayev, a third-year student in the group of Professor Georg Reifel within the physics department. Alisher is originally from Kazakhstan and obtained an undergrad degree in physics from Nazarbayev University there. And today, we'll be giving a presentation. So, Alisher, whenever you're ready.
Thank you for introduction, Max. And thanks everyone for coming, for joining in. In case you have any questions, feel free to interrupt. And today I'll be talking about a recent study we did in our group, of Professor Georg Reifel in University of Michigan, together with our collaborators in Shaanxi University in China, on predicting a novel Rydberg-atom-ion molecule. So it's relatively young research field, and I think it's necessary to give some introduction to the audience on Rydberg atoms and molecules. And after that, we'll talk more about interactions between ions and Rydberg atoms. It will lead us naturally to questions of how this molecule that we're predicting is formed. We'll ask more questions that are important from the molecular physics point of view about vibrational spectrum of the molecule, how you can form it optically, meaning using lasers in lab. We'll provide some comparison for about which atom to use, basically, whether rubidium or cesium or something else will be good. And I actually will also talk a bit more about why rubidium would be a good choice. And I'll conclude with a bit of discussion on future prospects for this molecule, or basically what would be interesting to consider in future studies. So it's important to, I guess, give a definition what is a Rydberg atom. And for that, I decided to recall a bit of the undergrad quantum mechanics. So let's recall the hydrogen atom problem, which is nothing but the basically a problem on motion of electron in the electric field of the proton. Usually, proton is located at the origin of the coordinate system, just it's easier. And then you have your usual suspect, the Schrödinger equation that you have to solve, where this psi is the eigenstate and E eigenvalues or eigenenergies. And so this, I guess everyone knows that this equation is not easy to solve. So this Laplacian operator will then have both radial and angular part, but it's good that it can be solved analytically, and then the eigenstates, the psi functions, can be described using, so radial part will correspond to associated Laguerre polynomials, and angular part will be spherical harmonics. But what is more convenient in the quantum mechanics realm, so to say, is to actually characterize the state using something else. And it turned out that there is a nice set of so-called quantum numbers that can basically describe the state of the basically hydrogen atom. And there are three quantum numbers. One is principal quantum number n, another is orbital L, and magnetic quantum number m. And another thing that you get from the solving the Schrödinger equation is that the eigenvalues, so eigenenergies in this case, they are inversely proportional to principal quantum number n squared. And so at least at this level of difficulty, it is what it is. But if you, I guess, will be solving more and more quantum mechanical problems in your undergrad classes, for example, and then you include, for example, relativistic effects, some spin orbit coupling, something else, then you'll get actually that energies become dependent on also L and M. So the degeneracy with respect to L and M quantum numbers is lifted, but at this level, eigenenergies are just inversely proportional to n squared. And this this dependence, so this dependence is nicely described, leads to a very nice Rydberg formula that I show here. So you can estimate basically the energy interval between two energy states using this formula. And there is this Rydberg constant. In general, I give this formula. It will appear later in a bit different context. But at this point, let's just stick to this formulation of Rydberg formula. And by the way, the wave function of hydrogen then might look like this. So in this very nice chart that I found online. So it reminds, I guess, everyone about some chemistry classes that you might have had. So for example, S orbital is usually it's just spherical. But our question is, what is a Rydberg atom, right? So far I talked only about hydrogen. So, but let's stick to this n quantum principal number. And if you manage to excite electron to to the state with high n, usually n larger than 10, then it's called the Rydberg state. And so basically atom with such highly excited electron is called Rydberg atom. So it's this rough definition. And this large n basically leads to exaggerated properties of your Rydberg atom. And they're all can be very nicely derived, again, using quantum mechanical approach. And outline here some of the most important properties. For example, the outer electron orbit radius, which roughly corresponds to the size of the Rydberg atom scales as n squared. And if, for example, n goes to higher than 10, for example, you can actually excite to n equal 100, then you get the size of the Rydberg atom to be 10,000 times larger than the atom in the ground state. So actually Rydberg atom can reach the sizes of almost micron or even a bit larger. And accordingly, the electric dipole moment also obviously enlarges, so it becomes enormously large. What is also interesting that the radiative lifetime increases, and it's also very useful for certain applications of Rydberg atoms that I will talk on the next slide. And also, you can imagine if the dipole moment is increasing, then the dipole-dipole interaction, they also scale enormously, and then it's very attractive for such applications as, let's say, quantum computing or quantum communication. And talking about that, so let's overview a bit of the modern research with Rydberg atoms. So as I said already, so the main kind of a word on the street is quantum simulation, quantum computing with the Rydberg atoms. So nowadays people can trap cold atoms in the arrays of optical traps, or optical tweezers as they called, and they can rearrange into arbitrary shape of these arrays. So for example, there's a French group managed to actually make a Eiffel Tower made of towers, so made of atoms. So you can see this shining green point is actually a single atom. So it's a very impressive experiments that can now lead to studies on non-equilibrium quantum dynamics and problems that cannot be observed, let's say, in the regular solids. Another important application of Rydberg atoms is precision measurements. So, for example, there are some proposals to measure the Rydberg constant that I mentioned before with circular Rydberg atoms. That's a bit different type of Rydberg atom, but basically, Rydberg constant uncertainty is called one of the reasons why there is this famous proton radius puzzle. And so basically, maybe Rydberg atoms will be useful in resolving this puzzle.
Maggie, did you end up getting keys for this office?
I did.
Okay.
Another important aspect of the of using Rydberg atoms for certain practical applications is a field sensing and control. So as I showed in the previous slide, the dipole moment scales enormously with n as n gets larger, and basically it means that the Rydberg atoms can couple to external fields very strongly, and you can basically make, for example, some sort of atomic radio made of Rydberg atoms. And one more important application of Rydberg atoms is modern, at least research, are Rydberg molecules and cold chemistry. So I have to say that applications of Rydberg atoms are not limited to these 4 categories I mentioned, but for the rest of the talk, I will mostly concentrate on that. And the next question one can ask is, so what is actual Rydberg molecule? And for that, I give the following definition. So Rydberg molecule is a bound state between 2 or more constituents, among which at least one is a Rydberg atom. So small disclaimer is that it's not exact definition, but I think it manages to describe what is a Rydberg molecule pretty nicely. And as long as you have this, as long as you have this guy with exaggerated properties, a Rydberg atom that already have some interesting stuff, you can imagine as long as you start to bind it with something else, you get even more exotic properties. And Rydberg molecules, they do possess such properties such as unusual wave function structures, or it has a large permanent electric dipole moment, which is was a kind of a surprise also, was observed. So electric dipole moment is measured in dBs, which is in SI units, it's Coulomb times meter, and 1000 dB it's enormously large. And another interesting property of Rydberg molecule is their large bond length. So meaning, basically, it's the large size of the molecule. It indeed can reach a couple of microns. And for example, on this plot, x-axis in atomic units, so it's usually Bohr radii, and Bohr radii, I can remind you, it's like a half an angstrom, so it's roughly half a nanometer. And you can imagine if it's 1,000 nanometers, then it's already a micron. It's indeed large molecule. And modern research with the Rydberg molecules now also led to rough distinguishment between different types of Rydberg molecules. So first type, this is the type that was predicted first and actually was observed first, as far as I remember. So there is a comprehensive literature on this topic. Is Rydberg ground molecules, so as they are called sometimes in literature. So this molecule looks like as follows. So we have a Rydberg atom with its large wave function. Here is the Rydberg atom nucleus, and this whole blue C is the Rydberg atom's electron orbital. And there is a ground state atom somewhere in the vicinity of this wave function. And it acts as a perturber, and as a result of the scattering of this ground state electron off the Rydberg electron, then you get a bound state. And the second type is so-called Rydberg macrodimers. So they're also called Rydberg molecules. And they are a bit different from the first type. In this second type, now we have two Rydberg atoms. We actually can have even more. So, but in this case, both atoms are very far from each other. Their wave functions don't overlap at all. But still, they can form a molecular bond through electrostatic multipolar interactions. And what is interesting is that actually our molecule that we are going to predict is very similar to this second type, but it has a different constituent, different second body there. But I'll talk a bit about this a bit later. But basically, the molecule that we are proposing will consist of the single ion and a single Rydberg atom, and they will form a molecular bond. So this studies of Rydberg atoms in external electric fields, it's actually a pretty old topic. So people did that, let's say, in 60s and 70s, and even at that time, in the calculated and measured, actual experimental as well, the Stark maps of energy levels of Rydberg atom. So here you have on y-axis you have energy in some units, and on x-axis you have electric field. So through Stark effect, you can see how these energy levels behave in the external electric field. And you can see sometimes here, I denote it was a red arrow. People already observed, and both in experiments and in theory, that you can get some sort of a potential minima, and you can ask a question. So what does it mean? So is there really some minima? If there is potential minima, then there gotta be some bound state. But this was in a uniform electric field. But what we ask the question, so what if this source of the external field is ion? And ion produces inhomogeneous electric field. So now the question is, again, is it possible to confine neutral atom in the electric field of an ion? And is it possible basically to form a molecule? And for that, we considered the following model. So we have ion, we have Rydberg atom. So here's a Rydberg electron here. And I have to draw your attention to the fact that they are located very far from each other. So basically, the ion is not in the vicinity of the Rydberg atom wave function. So we consider the following Hamiltonian. So actually, the actual Hamiltonian we used in our calculations is way more complicated, but one of the pieces of this Hamiltonian looks like this. So it roughly can be separated into two parts. So first part is a usual unperturbed Rydberg atom Hamiltonian that includes some fine structure and hyperfine structure. But what is important here is the second part, which corresponds to the multipolar interaction between ion that has to good approximation, it has only monopole moment that interacts with the electric multipoles of Rydberg atom now. So you remember that the Rydberg atom is large, so it has not only dipole moment, it has now quadrupole moment and high order multipoles. And so this interaction can be roughly expressed through this formula. So I'll talk about it a bit later. Just 2 comments about our model. So this big R is, as I said, is larger than the Rydberg atom radius. And the ion, so ion can have internal structure in general. It's important, for example, for this quantum computers based on the trapped ions. But in our study, we didn't consider internal structure of ion because it just doesn't add any interesting physics to that. So now we can ask how it's formed. So let's go back to this interaction term. So what does it consist of? So we have this big R that I showed. It's a distance between ion and Rydberg atom. A bunch of coordinates with E subscript. They correspond to Rydberg electron. And Y is spherical harmonics. It's also comes, I guess, from, you could have seen it in the hydrogen wave function. But all this guy is enclosed in the summation. And we have this summation over L, which are basically multiple moments. And it's important, it's interesting to visualize how these multiples look like. So for example, for L equal 1, it's just a uniform electric field. It corresponds to the charge distribution that produces uniform electric field. Now it's not enough, right? So you have to include more. So if for L equal 2, you get a quadruple electric field. And as you go further, you can imagine that things can get more and more interesting. They can get more and more nonlinear. And as you calculate, so you have your Hamiltonian, you diagonalize it, and then from that you can get a potential energy curves, as we call them. So they obtain it through diagonalization of the Hamiltonian. Then you get very interesting curves as they look like. So on y-axis we have energy. On x-axis now we have distance from the ions, which is basically, it also should correspond to electric field in some sense. But what we observe there is as we include more and more multiples, actually we went to L max equals 6, you get a very nicely pronounced potential wells, potential minima that also should remind you of this possibility that you can form a molecule within these wells. And so as long as you see them in the result of calculations, you can actually answer the question that I put before. So is it possible to form the molecular bond between ion and a Rydberg atom? So answer is yes, it is possible. The next good question that, for example, chemists can ask, so what is the vibrational spectrum of this molecule? And for that, we take a single well, for example, this one. So also I can draw your attention to the fact that you can see that as we include more and more multiples, these wells, they don't only get more pronounced, they also become more separated from other structures, and which is very nice for the experimental implementations. But for vibrational spectrum, we can take just the single well and calculate its eigenstates. And I have to also emphasize that these wells are very deep. So if this y-axis is in inverse centimeters, but we can convert it also to megahertz or gigahertz. So actually these wells are very deep. There are several gigahertz, and in atomic sort of, so to say units, it's really deep, and it means that this well can support many vibrational states. If you look closer, also these wells, they don't really look like harmonic oscillators that have some unharmonicity that actually lead to uneven energy spacing. So, and this energy spacing in the range of 20 megahertz, of like tens of megahertz, and this is very convenient for creating the vibrational wave packet. So for that, I prepared the movie here. Let's see if I'll manage to play it. Well, maybe not now. The fact is, if you try to play this movie, so what you will see is that this nicely localized wave packet will be moving. So this is not our system, okay? This is the system that corresponds to electron in the finite potential well. So it's shown in these dashed lines. But as long as you turn on your time propagation, you will see that this wave packet will start to move from well to well, and it starts to disperse. Basically, this nice Gaussian wave packet starts to disappear. You'll get a lot of maxima and minima. But at some point, it will revive, actually. And then you will observe again the formation of this vibrational wave packet, of this Gaussian wave packet, and this is called quantum revival. And this is pure quantum effect. You cannot really see wave packet revival in classical mechanics, if you consider some oscillator system. But in quantum system, you can. And our molecule is actually very nicely fitted for such a study. And also another thing that chemists can ask is actually, what is the rotational spectrum? What is the rotational structure of this molecule? So we estimated it roughly to be in the range of 1 to 10 kilohertz, and it's actually becoming challenging for current laser spectroscopy. So, but never say never, but it's a question for future. So next question then, from experimental point of view, you can ask, so how can you actually excite this, how you can form this molecule? And for that, we consider the optical excitation. So basically, you apply lasers to your to your cold atoms. And we are considering rubidium so far. I'll talk why we choose rubidium a bit later. But as long as you add this optical field to your to the region with your molecule, you can utilize also the time-dependent perturbation theory, or the consequence of it, the Fermi's golden rule, that allows to calculate the rate of photoexcitation rate, which is basically roughly should correspond how many molecules per second you excite for certain intensity of your laser. And this value, 10 to the 9 volts per meter squared, is pretty accessible in labs nowadays. So what we got is pretty high photoexcitation rates. So in these potential energy curves that I'm showing, you can see the red backdrop lines. So they're proportional to our calculated photoexcitation rates. And if you look, for example, to this side, you can see that these red lines are a bit thinner than here. And it basically means that on this side of the potential energy curves, the photoexcitation is larger. So it really means that so first of all, the photoexcitation rates themselves, they are large. So it means that it's really experimentally possible and feasible to observe these molecules in lab. And what is also interesting is that the excitation can occur on this outer well. So this is, if we call this inner well and this outer well, the excitation of molecule might happen somewhere here, and then molecule should adiabatically fall into this potential minima. And one more comment on the possible experimental implementation. So we consider different initial states from which you can start Rydberg excitation. And usually, so more popular states now in the experiments with rubidium are 5p 3/2 or 5p 1/2. They call D2 and D1 line correspondingly. But what is interesting, actually, for this initial state being 5p 3/2, we got photoexcitation rates lower than for some more exotic initial state, which is 5d 3/2. So we're doing currently a lot of experiments on this state in our lab. So basically, it means it should show that in your experiment, you may be better try to use 5d 3/2 state in rubidium. But it's more a question for future experimental efforts. The different question you might ask, why are you talking always about rubidium? And for that, so I actually found a very funny phrase by William Phillips, a Nobel Prize winner in physics from 1997, that rubidium was a God's gift to Bose-Einstein condensate. And here I show the corresponding picture. This is the first Bose-Einstein condensate that was obtained in University of Colorado Boulder by the group of Carl Wieman. They got a Nobel Prize in 2001 for that. And it was done with rubidium, and rubidium is in general, it's a very popular alkali atom in laser cooling and trapping experiments. Another one is a cesium. And why it's so popular is actually because rubidium has a very convenient energy level structure that is suitable for ionization. For example, you can use ionization. So for this molecule, you need to create ion, and you need to create Rydberg atom from your sample of cold atoms. And basically, in rubidium, you have all of that. And you can do that just with lasers that are commercially available. So you can create ion this is the level structure for future experiments that we suggested in our paper as well. So you can create ion here, and you can create Rydberg atom, and here you go. Then you look for this molecule by a suitable detection scheme. And what is, I guess, even more important in this case, so rubidium has a suitable quantum defect. And so this quantum defect is maybe something new. And there is a nice overview of the quantum defect theory. Roughly, it can be summarized in the correction to the Rydberg formula that I showed before. So it was nonlinear already, right? So before, but here, if we look closer, so here we added these red deltas. So these red deltas are basically they change effective n principal quantum number. And why is that? Is because, so if you look at the periodic table, rubidium doesn't have one electron, it has several electrons. Yeah, it has one electron on the outer shell, but it has more protons, it have more neutrons, it have more other electrons, and they all interact with each other. And basically, it leads to certain effects that basically lead to necessities, or so to say, to correct this Rydberg formula. And it turned out smart people found that you actually can do that by introducing this more empirical functions of delta, functions delta that depend on n quantum principal number and L. And then you can get something interesting. For example, these quantum defects turned out very important for the formation of this molecule that we are predicting. So the details are a bit more technical, so I'm not going to talk about them today, but please look at our paper if you're interested. But these deltas, they can be measured experimentally. For example, we recently published a paper where we measured the NG quantum defects. Basically, G corresponds to L equal to 4. And so you can do that spectroscopically and then use for your calculations, which is very nice. And as I said, so another popular atom is cesium, and so it's very natural to compare. So which atom would be better to use? Was it rubidium or cesium? And it turned out it doesn't really matter. They're both pretty good. They have suitable quantum defects both. And here we show the calculated potential energy curves on the same energy range. And you can see that these molecular potentials, they look pretty much same. Maybe one note is that in cesium, you have these curvatures. Curvatures of this potential, they translate into so-called non-adiabatic effects that can lead to the decay of the molecule to other potential wells. And then as long as it decays, it's basically lost. And for cesium, it turned out that these curvatures of this potential wells is such that cesium Rydberg-atom-ion molecule might live a bit longer than rubidium, but from experimental point of view, it's a bit more challenging to work with cesium because it's a bit challenging to get a Bose-Einstein condensate of cesium. But in any case, it doesn't really matter if you have rubidium or cesium in your lab. Both should give you this molecule in your spectroscopic signal. And for that, at this point, I would prefer, I guess, to finish my talk. So what we did, we proposed a novel type of Rydberg molecule. We devised the method for its optical excitation. We predict that it should be very stable against adiabatic decays, meaning this molecule would be very long-lived. And it opens a lot of roadmaps for future experiments and maybe applications of this molecule for something else. And future work might include detailed calculations of lifetimes, vibrational wave packet dynamics that I mentioned, looking for this Rydberg-atom-ion molecule in other systems, such as maybe other alkali atoms. For example, there is sodium, there is potassium, there are alkaline earth atoms that are also very popular nowadays. For example, strontium, the most accurate and precise atomic clock in Gila, for example, is made of strontium in optical lattice. So, and by the way, Rydberg molecules also were observed in strontium, in cold strontium atoms. So one has to do maybe more calculations there. And one could actually start already the experimental efforts for spectroscopic observation of this molecule. And so the presented work is published at PhysRef Research. It was published a couple of months ago. And just a teaser or spoiler, we continue working on this molecule. We already have some preliminary data on the on what is the lifetime of this molecule, depending on different principal quantum number and different vibrational quantum states within for fixed quantum number n. And so on the y-axis here on this panel, the y-axis in milliseconds, and you can see that, for example, the ground vibrational state, it's by convention, it starts from 0. It should live for n equal 45, should live about 120 milliseconds. I have to say it's very long. Actually, funny thing is that the Rydberg atom at n equal 45, its lifetime is roughly a couple of hundred of microseconds. So actually, Rydberg atom will decay first, then the molecule will dissociate. So it means that the lifetime of the molecule that we're predicting should be limited only by the lifetime of the Rydberg atom. And there are some interesting effects that also happen. For example, you can see overall we observe that the higher vibrational state you pick, the shorter lifetime becomes. But first of all, these lifetimes never reach smaller than a couple of milliseconds, which is good. And we observe some jumps here, which basically indicate some presence of quantum interference in this molecule, which is also might be worth more detailed study. And also additional panel that I'm showing now here, y-axis in seconds, not milliseconds. They are, by the way, logarithmic axis. And we plot here the lifetime of the ground vibrational states for different now Rydberg states. And you can see overall this decay with n is predictable. The larger your n, the faster its lifetime will decay due to some certain reasons, but we observed a very interesting jump somewhere n equal 55, and we want to look at this closer. What is this? So you can see that there is a lot of room for research and scratching your head of how it can be applied for real technology, for future quantum technologies. So at this point, I want to thank my research group, our PI, Georg Rethel, grad students, Ryan, Benit, we have a couple of undergrads, Ansh and Abby, who is RU students, and our alumni, who also were actively involved in this study, so Michael, Lou, and Jamie. And our obvious collaborators from Shaanxi University, with whom we published this paper, Shao Shan and Jian Min. So these are our funding agencies, and for whoever is interested in cold atoms and AMO in general, we're looking for new students. Feel free to get in touch if you're interested. This is my email and this website of our group. And at this point, I want to finish, and I'm ready to answer any of your questions. Thanks for your attention.
Thank you very much. I'll stop the recording in case people want to ask a question.